So today I will be doing 2.3 of the electrostatics homework number 1, and the problem is as followed. What is the electric field at a distance x away from the center of a thin line charge with a uniform linear charge density lambda and length L? See diagram below, which is A. And in part B is using the result, write the electric field at a distance x away above the center of a square loop of length L. So this problem is, the first thing that I would do is probably just draw the diagram again, just to make it easier to see. So I'm interested in this point right here, and trying to ask for the E field. And we know that this has a charge density of lambda. Now, we know if we're looking at, if we call this D, if we call this y, axis y, and call this axis x, then we can, if we look at a small little dy, we know the electric field will look something along the lines of this, and the same electric field will go on the other side too. dE, because it's coming from a small dy. So the question comes, what is this dE? Well, we know the equation for that. dE is simply just equal to k dq over r squared. And this is dE right here. But what is dq? dq is simply just the lambda times our dy, because lambda simply just represents linear charge density, which is just charge per unit length. So if we multiply it by our length, or dy, we can find the amount of charge, or our dq. So it's important to remember that this is a vector. So that means we need to break this into components. So what components are we interested in this case? Well, I like drawing the components out. So for this vector right here, the components will look something like this. And then for this vector down here, it will look something like this, with the same arrow going this way. So that just means that since we know that this is our y-axis, since that's stated right here, these will cancel out, and all we are left with is the x component. So that just means that we are interested in the x component. So if I know, if I call this angle theta, sorry if that's hard to see, theta, then that also means that this angle is theta also. But all that means is our x is going to be cosine, because theta is right here. So that means on our x-axis, it's going to be cosine. So since we know that we are only interested in the x component, then dEx is simply going to be equal to dE times cosine theta, and this is our theta. I'm sorry this is hard to see, but yes. So just to reiterate, our y components cancel out, so all we are interested in is the x component. So to find the x component, we need to figure out if it's cosine or sine, and to figure out if it's cosine, we look at the angle, and I decided that this is my theta, so that means my x is going to be cosine. So dEx, the x component of our dE, is going to be dE times cosine theta. So next, I'll simply just plug in what we have here. So dEx is just going to be equal to dE, so k times dq, which is lambda, multiplied by dy over r squared times cosine. And we can just look at this theta because these are the same angles. So if I call this x and r, then all that means is cosine is simply equal to adjacent over hypotenuse, or x over r. So x over r. So now I decided to take the integral on both sides. So integrate then we are just going to be left with EX is then just equal to the integral. And what is our limits of integration? Well, because it says that this whole length is L, then this one, we can call this L over 2 to negative L over 2. So our limits of integration will be from negative L over 2 to L over 2. So negative L over 2 to L over 2 times this whole thing inside. So just to simplify this, to make it easier, we know that k is a constant, lambda is definitely a constant, and x is a constant as well, because this point is not moving. We're interested in finding the electric field at this point, so x will always be the same. So I'm just going to make this nicer, E of x would then just be equal to k lambda times x, the same integral, negative L over 2 to L over 2 dy over r cubed. I simply just moved out k, lambda, and x and multiplied the r squared and r. So I'm just going to rewrite the same integral again just so that we don't get confused. K lambda x negative L over 2 to L over 2 dy over r cubed. So now we need to solve this integral, and this is definitely going to be trig sub because the power on the numerator is 0. If you have nothing on the top, then that means we use trig sub. So trig sub, how do you do trig sub? Well, first, the way I like doing it, well, is drawing the triangle that we are using. I am just going to redraw this triangle right here. So the triangle looks like this. Theta, r, x, and y. And now the second thing is to relate the variable with our constant. So the question comes, and what is our variable in this case? Well, once you think about it, x is our constant, as I said before. Y is going to be a variable because this dy can be anywhere. So if we cos angle y, this length y, then dy can be here, 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 here. It doesn't matter. That means our y is going to be changing. So that means, how do we relate our variable with our constant? So So we need to relate our x with our y. X in this case is adjacent, and y is our opposite. That means we have to use tangent. So tangent of theta is simply going to be equal to our opposite, which is y, over adjacent, which is x. And now solving for y, we get x tan theta is equal to y. And now taking the derivative of both sides, we get x secant squared theta d theta is simply going to be equal to dy. So now the third step is to relate radical with the constant. So our radical, which is just the hypotenuse, is r. So how do we relate our x with our r? So this term is adjacent and this term is hypotenuse. So cosine. So cosine theta is going to be equal to x over r. So now solving for our r, we get r cosine theta equal to x, or r is then just equal to x over cosine theta. So now we can just use these two terms to plug it back into our integral and then solve for it. So just rewriting the integral. So I'm just going to replace our dy with x secant squared theta d theta and our r with x over cosine theta. So we will get something like Ex is then just equal to k lambda x x secant squared theta d theta over x over cosine theta cubed. I simply replaced our r and dy with the stuff we saw for before. And this is simply just going to be x cubed secant cubed theta. That means Ex is just going to be equal to k lambda x negative L over 2 x secant squared theta over x cubed secant cubed theta d theta. And it will just cancel each other out, and we are just going to be left with 1 in the numerator. So Ex would then just be equal to k lambda x negative L over 2 to L over 2 1 over x squared secant theta d theta. And if this integral is still confusing, we can always take out this x squared because x squared is going to be a constant. And then so Ex and secant is simply just going to be 1 over cosine theta, which means that it will just be cosine. And now we just integrate, and the integral of cosine is just going to be sine. So E of x is just going to be k lambda. Our x's will cancel out, and we're just left with x in the denominator times sine theta from L over 2 to negative L over 2. We can't just plug these limits back in here, so we have to relate it back to our triangle. So if we have So relating it back to our triangle, you know sine theta is just going to be simply just going to be opposite over hypotenuse. So y over r, and r is just going to be x squared, square root of x squared plus y squared. So we will just get E of x is then just equal to k lambda x times y over x squared plus y squared from L over 2 to negative L over 2. And this term was just r. So now we can just plug in our limits of integration. And if you don't remember what to plug it back into, just remember that we were integrating with respect to dy. So that just means we just have to plug it into y. So that means we will get Ex is then just equal to k lambda over x times L over 2 over x squared plus L over 2 squared, that's a 2, minus k lambda over x times negative L over 2 over the square root plus negative L over 2 squared. And to simplify this, it's going to be, if you look at L over 2 minus L over 2 would just be L. And simplifying this part, it will just be L squared over 4. So, E of x will just be k lambda L over x times the square root of x squared plus L squared over 4. And this will be our answer for part A. So now, moving on to the second part of the problem. The second part of the problem is simply asking, using the same result as we got in part A, write the electric field at a distance x above the center of a square loop of length L. So I'm just going to redraw the diagram. So this is for part B. We draw a diagram, we have something like this. Boom. And then right at the center, we're interested at this point right here in finding the E field at an x distance away. And we know that this is length L, so this is just the wire that we are working with in part A. So if I was looking at a little segment of this wire, it will create an electric field like this. And then, if you were to think about it and draw the same electric field on all four sides, you will realize that the y components, like the problem from part A, actually still cancel out. So if we draw this, we realize the components will also cancel out, and then the components from here and here, the components will cancel each other. The y components will all cancel out. So all we are interested in is the x component. So, E of x would then just be equal to E cosine theta, where E, we can just use the E from part A. So, plugging the E from part A, E of x would then just be equal to E, this E of x will be then equal to this E over here. So, it will just be k lambda L over x times square root x squared plus L squared over 4 times cosine theta. But you have to remember that we have 4 electric fields coming from all 4 sides of this square. So we have to multiply it by 4. So now this might be a little bit confusing because we just copied what we had from part A. But this x is not the same x as we drew for this diagram. This x for part A represented the distance that the point was away from the wire. So if we call this distance r, this vector r, and we call this L over 2, and then we know that this angle is theta, then that just means that Rx in this scenario is going to be R, because this represents the distance at this point is away from each wire. R, 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 and R. So in this case, X is really equal to R, which is just equal to the square root of x squared plus L squared over 4. So we simply just have to replace this x with this term over here. That means E of x would then just be equal to 4 times k lambda L over, replacing this x with this term, we will get x squared plus L squared over 4 times the same thing, and replacing this x again. If we plug in the square root of x squared plus L squared over 4 into here, the square root will go away. So all we're left with is what's inside. Plus L squared over 4 times cosine theta. And in this case, what is our cosine theta? Our cosine theta will just be adjacent, which is our x, and then over our hypotenuse, which is r. So if obviously we draw the triangle, we have something like this. X, this part is L over 2, and r. So it will just be x over r, and we know r is simply just equal to x squared plus L squared over 4, and square root of that. So E of x is just going to be equal to 4 times k lambda L over the same thing again, x squared plus L squared over 4 square root of x squared plus L squared over 4 plus L squared over 4 times adjacent over the hypotenuse of r. So times, so I'm running out of space, x over x squared plus L squared over 4. So this will be our answer for part B.